And the same is true also, I think, with the driver reaction time. People will take longer to react, so there will be wasted time in the system, and the efficiency would be lower, and therefore the capacity would be lower. Maybe I'm just thinking of it another way, but saying the same thing.
I think you're right. But for mean headway, it may not be a...
The mean headway, I think you're absolutely correct. It's direct function of the volume. So if the headway is, yeah.
Okay, thanks. So Adele actually taught me about these concepts. So feel free to select the travel flow theory class if you want to know more. Okay, we have finished talking about these parameters. These are only 3 parameters that are selected, and you will be able to find more parameters. The reason I list them here is that I want to promote you thinking about these effects, their effects. You may not need to remember those functions, but you have to understand them in a qualitative way. Now let's talk about signalized intersections. I also listed 3 parameters here. Startup loss time. This is easy. Startup loss time means when you are waiting at an intersection under yellow signal, under a red signal. When the signal becomes green, it takes you 1 or 2 seconds to start moving, and that's called startup loss time. Then how does this affect capacity? So when you lose more time, you lose more capacity, right? This is easy. The second parameter is called discharge headway, which I already introduced. How does this discharge headway affect capacity? That's also easy. Somebody answer it. When the discharge headway goes bigger, which means the vehicles will discharge at a lower rate, then this capacity, the capacity of the intersection, will be lower too. So it's a negative relationship. The third thing is gap acceptance for unprotected left turns. This is similar to that. So unprotected left turns will block those through movement if they could not get a sufficient gap, right? So that's very similar. These are parameters that you may want to choose for calibration. When you're calibrating your model, you may not want to select all the parameters for calibration. I think most of the time you divide more parameters into 2 sets. One set for not to be calibrated. The other set for to be calibrated. And you don't want to select all the parameters for calibration because that will dramatically increase your search space. Well, here's a small problem. Let me solve it. Okay, the fourth step is to set calibration objective function. And now you want to calibrate your parameters, and you have 2 sets of capacities. But you don't have any, you have to have an objective function, or a function, objective function. And so that you can quantitatively measure this difference. And you have 2 options for that. The first thing is already learned. I think you already learned from your statistics class. It's called root mean square error or root mean square deviation. I think you understand this, right? So we have 2 vectors, and for each element in the vector, we calculate their difference, and we square the difference and sum them up, and then calculate the square root. That's called root mean square error or root mean square deviation. The second possibility is called GEH, which I'm going to introduce later. And here is another thing called the coefficient of variation that I think you should know, but this is not an objective function. The coefficient of variation is defined by the standard deviation divided by the mean. is used to measure the variation of a series of numbers. The reason that we need it is because we may want to run our model several times. And because we run the stochastic model several times, we may not get the constant result. And we want to measure the variation of several runs. So that's why we need this CV. So if we only use the standard deviation, we can already describe this variation. But the standard deviation cannot be directly compared. Because if you scale your data to 10,000 times, 1,000 times, then your standard deviation will also increase. So you cannot say the standard deviation is the smaller the better. But if you divide this by the mean, then the two series will be comparable, right? Clear about this? Now let's talk about GH. What is GH? GH is named by its inventor, whose name is GH, and it was invented in the 1970s. This is a transportation engineer in England. The function, the purpose of GH is to compare two sets of traffic volumes. So it was originally developed for transportation, to compare volumes, traffic volumes. The formula is GH is equal to square these things and this thing. And there are two vectors. The first vector is two numbers. The first number is the simulated volume. The second number is the real world volume. So you can calculate GH using this formula. And if the GH value you get is less than 5.0, then it's considered as a good match. So two volumes are a good match. Let me use another figure to show you why. This is the target volume. So we can say it's the real volume, the target volume, real volume we want to get. So this is 10, this is 0, 5,000, and it goes to 50,000. So this is volume, like per hour, vehicles per hour. This is the maximum variance allowed. So if we use 5%, it will be straight line. When the volume is low, the allowed variance is low. When the volume is high, the allowed variance is also high. So it's a linear relationship. But when you use GH equals to 5, when the volume is very low, it allows a lot more variance. But when the volume goes high, it allows less variance. This pink curve is GH. All right. We can use this, and it's recommended in FHWA guidelines. So I want to introduce it. And this should be which is the next step. Let me show. So this should be the 5th step. Sorry. Numbering. Okay, after we get the objective functions, we have to perform a search for optimal parameter value. And this is called nonlinear, because your model is nonlinear. Nonlinear least square optimization problem. This problem is not easy to solve. It can be categorized as two types. The first type is called single parameter search, which means you only have one parameter to calibrate. Then you search for it. But in most of the case, you have multiple parameters to calibrate. So you're going to perform a multi-parameter search, which is more difficult. Right? To search for multiple parameters, we typically use heuristic algorithms. Because of this nonlinear relationship or nonlinear calculation, it's very difficult for you to solve this problem backward mathematically. So we use heuristic algorithms. means these are not going to give you an optimal solution for sure, but they probably will give you an acceptable solution, and it will be much faster. But it's still time consuming, because the heuristic algorithms typically requires you to run the model several times, like thousands of times at least. And you will need a lot of coding, so you have to use your own code to run the simulation model. So it's not very easy. Then the next step is called fine-tuning. So in this step, after calibrating all these global parameters, you can modify some link-specific parameters, like link-specific capacity adjustment factors. And if this is provided in your tool, you can use it. So first, global optimization, global tuning, then fine-tuning. Now let me give you an example of single parameter search. This is easy, but I want you to see some points. So you change the mean head weight, for example, to 0.1, and you run the model several times. Not only one time, but run the model like 4 times, and you get 4 mean square errors. This is your objective function. Here you use mean square error. Is equal to, it's the square of root mean square error. So basically they are the same thing. And you change the parameter, and at each parameter, using each parameter, you run it 4 times. And then you can create a curve. You can plot a curve. And in this way, you may be able to find the optimal value. So this is single parameter search. It's easier. But let's talk about multiple parameter search. Let's assume you have 2 parameters, only 2 parameters. And this will be much more complex, because your landscape, your fitness or objective function landscape may be very spiky. Sometimes it may be very smooth and very flat. That will be easy for you to search. But let's assume this function. Let's assume in this function you have one parameter, the other parameter, and the z value means the objective function, the result of objective function. Now let's assume, for example, let's assume we are trying to find the smallest objective value. Then how can you search? How do you perform the search? Let me first introduce to you these heuristic search algorithms, HSAs. We first have to know this NFL theorem. NFL, no free lunch, not National Football League. NFL theory.